everybody. I'm that guy he just introduced. I'm going to talk about a possible future of bare metal, because I obviously can't predict the future. But I can look at what works and what doesn't work in the current way we do things. Take a very big step back. This talk, or the title of this talk anyway, was inspired by Sean Parent's A Possible Future of Programming, which, if you haven't seen it, is one of the best talks on software ever. In that talk, Sean went into problems in GUI design. The Adobe bug tracker, and gave some statistics on what percentage of bugs at Adobe were GUI related, and it was somewhere 75% or something. And then they completely rethought how they're going to do GUIs, and they took a lot of problems off the table. And I think the result was something like 5% of the bug crack was GUI after they were done. People had to get used to programming in a very different way, but it solved the problem. I kind of got bored in sort of normal introductions of myself, and so I'm making a superhero origin story introduction of myself. It's not very super, but yeah. Because I didn't start as Odin the Nerd, I actually started as Odin the Hippie. I was born in a hippie commune in the middle of the woods, and this talk's also about abstracting things. So this is kind of the root of the abstract hippie. It's Don Quixote, the Spanish knight who went crazy and started fighting windmills. And this is kind of a root that all hippies share, and that they want to make things better, and they really want to do the right thing, but they're really misguided about how to do it, right? So they fought a bunch of battles about living in the country and anti-nuclear and who knows what, which are debatable results. But me, in sort of this hippie, I kind of saw a lot of people running into windmills, and so as sort of a thought experiment, I thought, well, okay, what if we could clone the world and then roll back our local repo 300 years at least worth of technology, because they had JIT back then, right? No, you roll it back 300 years, and then 95% of the world's population dies. Therefore, essentially, advancing technology is one of the most philanthropic things you can do, right? So there was a whole, giant metamorphosis thing, and Odin the Hippie became Odin the Nerd. So you can find me as like Odin the Nerd at Twitter and LinkedIn and Google Mail and Blogspot and whatever. I actually almost lied in my bio, because I actually haven't been a C++ programmer for 15 years, although I have been doing embedded development for 15 years. A lot of my embedded development, I saw myself more as an electronic engineer, looked a lot like this. And I did awesome stuff in assembler, and I wrote awesomely efficient programs in assembler. And I never really had a proper software education, so I did really weird shit in assembler, right? Problem was, A, no one else could read my code, and B, after enough time I couldn't read my code either. And I shot myself in the foot a whole bunch of times. And so at some point, I had this bug that I was looking for. Like, randomly, 1 in 1,000 chance some buffer was getting corrupted. And I had been looking at this for like 3 weeks, and I hadn't found it. Because, it was on one of those microcontrollers when you only get 2 breakpoints, and, you can't, like, trace anything, and how, it was intermittent. It wasn't, So I had a friend of mine helping me look, and we realized, okay, the corruption point, you'd see about 2 corruptions a day or something, trying to catch them in different ways, and then we found the corruption, okay, well, 3 times it was always on the same spot, right? And so I grepped for, well, I didn't know how to grep back then because I was a Windows kid, but anyway, so I searched for like that address, and I didn't find find it anywhere in my memory map, because you manage your memory yourself, right? I guess anymore you can theoretically look like a script, but yeah, like back then, yeah, I was managing memory myself, and it turned out it was like a calculated offset address where I had just accidentally typed a 1 in front of what it was supposed to be. And this was in this circular buffer where the reader would chase the writer actually quite, well, depending on the state of the program, but sort of at the state where this variable could be changed, the reader and the writer were always very close to each other. And so the probability of that actually corrupting data was very low. And my friend gave this sort of offhand comment that if I was using a real programming language, that couldn't have happened. And that kind of stuck with me. So I started programming, well, first I started with C, which I was very unimpressed with, because there was a whole lot of stuff in C that I couldn't do anymore, that I couldn't do with assembler. Because, as I said, I did really weird shit in assembler. Look at this call. After this call, there's an unconditional branch, right? So how do you ever reach this code? Well, basically, this was my way of returning an optional. I mean, where you're returning to is a register which is accessible. So I just returned to wherever I came from +1 in the success case, and wherever I came from in the fail case. And it was actually super efficient, right? You'd have to keep track of which function had this calling convention in air quotes. But it actually worked quite well. I didn't have to check data because I also didn't have a stack, so you couldn't really return things. But that's another, yeah. So then I, looking at C++, I asked my friend, like, yeah, okay, this is crap, because I can't do a whole bunch of stuff, but I can shoot myself in the foot almost just as easily. Like, okay, I have to use a stack. I can't corrupt it very easily. That's good. Okay, but like I can, screw up pointers. I can, yeah. And he gave me Andrei Alexandrescu's book. I'm not sure if he hated me and he told me this is C++. Well, try your hand at that. So I read Alexandrescu's book, and then I spent many years trying to create the same super efficient assembler that I used to be writing, but in a safe way in C++, which led me kind of straight to metaprogramming. And then I had something written, and it was kind of working, and I said, oh well, I should go to a bare metal conference, and we'll talk about this with other bare metal guys. There wasn't a bare metal conference, right? Because embedded world is basically just, if you want to talk to marketing people, that's a great place to go. I don't particularly like to talk to marketing people because they don't know what the hell they're talking about. But yeah, I wanted a bare metal conference, so we started a bare metal conference. And the first EMBO, which we didn't even call EMBO, I think 4 people came. Out of the 20 I invited that I'd found on the internet, and it was free, and only 4 people came. But last year at the EMBO, we had about 50 people. This year, we're aiming for somewhere between 80 and 100. And last year, we had 1 day, 1 track. This year, we have 2 days, 2 tracks. Yeah, it's in Bochum. It's coming up in, a month? A little less than a month. We still have some tickets left. Last year at the EMBO was very much hardcore library developers, people talking about template metaprogramming, people talking about sort of very, very low bare, foundational stuff. Because as we'll see in this talk, once you start to drill down and say, okay, can I build on this? Like, is this really going to work all the time? Right? Is there no scenario where this is going to break? Or are my assumptions about this library, are they going to be fulfilled or not? Or am I using something the wrong way? I mean, as a hippie, I've seen a lot of people use tools the wrong way. So duct tape works for everything. Anyway. So we were basically tearing down the world and throwing out everything that you couldn't build on. And that was fun, but it wasn't so much for sort of the casual viewer. This time around, we actually have some things that we're building back up. And we're going to go into some of them in this talk. But first, let's look at some of the problems that we have, right? Like what's hard in embedded? Because embedded is a different beast. Oops, clicker, oops. Damn, clicker's an embedded device too. So we have race conditions, but we have slightly different race conditions than other people because we have interrupt service routines, right? Interrupt service routine, if you're not familiar with it, is essentially a call that can be injected anywhere. It'll just be on your stack as if you had called that function, even though you didn't call that function. And that's okay. Like, it gives your stack back when it's done, so it has to run to completion. It can't, like, task switch or anything because it's on top of somebody else's stack, right? This has the advantage that interrupt service routines are very, very fast. If you want to say, okay, after this thing happens, I want to, within so and so many instruction cycles, do this other thing, you can start to make guarantees about that. Because on a scheduler, you can't, right? I mean, as soon as you want to be more fine-grained than the task switching frequency in a scheduler, you're pretty screwed, right? And even then, you know, what if multiple people want to do that? What if there's locks? Whatever. Well, yeah. But with interrupt service routines, you can get interrupted anywhere, right? I mean, this doesn't really look like a race condition. Okay, they're both masking some special function register, and they're changing different bits, right? If you're not so into bit tricks, this is clearing one bit, and this is setting one other completely unrelated bit. And that's another problem with bare metal. I've done a lightning talk on this a couple of years ago. Eventually, I'm going to do a full talk on this. We've also solved this problem. But anyway, bit tricks aside, this operation is essentially, it's not atomic. It's essentially multiple operations. Most cores, you'll have to read something into a work register, some kind of local storage. Then you can modify it, and then you can write it back again. This might even be 2 instructions as well, depending on your core. But that means that into the middle of this, an interrupt service you could fire, right? So we take a local copy, the original gets modified, we modify our local copy and write it back to the special function register. And if you try and get into like how do we solve this problem that this can happen, right? I mean, basically, the most common strategy is programmer discipline. I mean, programmer discipline is a myth. It's an excuse for writing bugs. But you basically punt to the programmer and say, don't do that, right? Or you know, or don't share, right? Well, I mean, the problem is these special function registers, they are global state, right? They're essentially RAM addresses that are wired to the hardware. So if you're getting data over a serial port, you're going to have some, you know, RX register, some input register, where every time you read from that register, you get the next byte that came in, right? Or you have configuration registers that set the baud rate of that thing, or whatnot, right? So these things are shared. We can't get around sharing them. Like, they're globals. We could turn off interrupts, you know, turn them off here, turn them back on there. But that's, for one, probably more than doubling the cost of this operation. It's also increasing the latency of interrupts in sort of an unforeseeable way. You know, you can't really know how long, what the maximum delay is, how long could this interrupt be off for before I can come back in. I mean, this is a great piece of trivia. I mean, because these registers are not RAM, you know, if you read twice, you're not going to get the same thing at the end of a FIFO buffer, right? We need to mark them as something weird to the compiler, which we do with the volatile keyword. When we're turning off and on interrupts, we're usually setting a bit in some interrupt. a control register, which we mark volatile, so that the optimizer doesn't say, oh, you're setting it and then you're clearing it. Well, I'll just clear it, right? So if we have, like, turn them off, 3 instructions, turn them back on, what's the longest that this interrupt can be off for? Well, the problem is that volatile means, the semantics of volatile are that the compiler cannot reorder two volatiles past each other. It can reorder non-volatile stuff past a volatile. So it could theoretically put your entire program in there. It probably won't, but it could, right? So you could have a hugely long wait on your interrupt, and you're never going to find that debugging unless you try and debug release builds, which is always fun. So yeah, this is the source of a lot of pain. There is a way to do an atomic operation and sort of a compare and swap operation, but it's very seldomly used, and when it is, it's usually wrong. Like, you can Google for that assembler instruction on, or you can search for it on GitHub and do statistics of how often it's wrong, right? Which is about 50% in my search 2 years ago. Because it's mostly just students trying it out. Like, in practice, relaxed atomics are something we leave up to like 10 people that still sometimes get it wrong, and electrical engineers programming microcontrollers. Because, yeah, right? They have excellent programmer discipline, I'm sure. So one of the solutions that we've come up with so far was to wrap all hardware interaction in a domain-specific language. So we take the machine-readable datasheet, generate templates out of that, which describe what this register does. Is it the end of a FIFO? Is it have some clear on read bits? There's all sorts of weird, I think hardware developers have a very black sense of humor and hate programmers. Yeah, so there's all sorts of weird stuff that can go on when interacting with the hardware, but our domain-specific language knows all of that and can magically make things atomic if you tell it to make it atomic, right? It gets a little crazy on the M0 from the Cortex M0, which doesn't have a compare and swap. But everything else we can get, pretty reasonably atomic. What are the problems we have? Well, we have out of memory, right? And out of memory is a problem that we have in other domains, but the accepted solution is very different, right? I mean, if you run out of memory on a desktop, you can just say, I'm out of memory. Pop up a little dialog box and then go back to the operating system. But like, where's the dialog box, right? I mean, it's sort of in the embedded use case, you can't even wait for user input, right? Like, that $1 billion worth of equipment is not going to wait for some microcontroller that went out of memory for somebody to go push buttons on it. Like, there has to be the guarantee that it's going to come back up and be operational within X amount of time and be in some defined state, right? Essentially, you have to guarantee that it's in a defined state at all times. Because as soon as it's in an undefined state, well, that's undefined, right? It could infect other things and put them in an undefined state. Essentially, the entire system has to be in some defined state at all times, come what may. And so that that makes our error handling much, much, much harder. Because, the sort of wussy desktop programmer error handling, you basically don't want to leak resources that are not RAM, right? I mean, worst case, you crash, as long as all the stuff you leaked was RAM, you're good. If you leak like named blocks or network sockets or something, then maybe not so good. But that's a pretty low bar. And if you start to get into this level of requirements, this level of guarantees that you have to make, proving that the error cannot happen or making your architecture such that the error cannot happen is usually easier than handling the error. We have different kinds of out of memory, right? We have out of heap. Well, okay, let's see. How many people here program microcontrollers or program sort of embedded systems in general? Okay, 50% or so. How many of you would bet your year's salary that you cannot run out of heap in your program? Okay, you don't earn anything, so voter. Oh,
I don't use no heap.
you don't use a heap. Okay, that's cheating. That's actually one of the right solutions. But yes, I mean, usually when I'm talking to people that use a heap, no hands go up. But implicitly, your employer is betting a similar sum of money that you are not going to overflow the heap, right? So, yeah. So, I mean, you know, how do we even say how do we prove that we're not going to overflow the heap? We make it big enough. Well, how big is big enough, right? I mean, the problem with the heap is, you know, depending on like use patterns, we, you know, allocate blocks and then we start to release them again, and we allocate more blocks. I'm going to try on this side. Okay, we allocate more blocks. Oh, this is working better now. And, you know, for example, this block here, it couldn't go there, so it's got to go over here, right? So we got a gap. We got another gap. We're, you know, maybe 50% full or something, but the next block doesn't have anywhere to go, right? This is, you know, a fragmented heap, if you will, right? And, you know, the absolute worst case heap fragmentation is so hard to calculate because it essentially depends on the timing of your program and the object sizes in your program and the amount of each of those object sizes that you're going to allocate, that essentially in sort of safety critical systems, you're just not allowed to do that, right? Like, you know, a pretty famous example is the Joint Strike Fighter coding guidelines, no allocations after takeoff, right? Well, if you think back to like the robots on the assembly line, there is no before takeoff there, right? Like you always have to work correctly. Yeah, so a lot of the time we don't use a heap. But that's, I mean, so where do you put the stuff that would otherwise go on the heap? Right, well, we're going to get into that later. I'm going to go into sort of other methods. Oops, whoa. Okay, everything going backwards. Okay, so we have stack overflow, right? We, you know, stack goes up, stack goes down. I don't know what that is, but it's probably one of the things that I'm talking about today, okay? Okay. Going back. Or screw this thing. Okay, so yeah, stack, right? Goes up, goes down. At the point where it goes up too far, then we're out of stack. But it could be more complicated than that, because at the deepest point of stack, right, here, we could be interrupted at that point, and the interrupt stack goes on top of that. And theoretically, another interrupt could interrupt that interrupt and grow the stack yet still further. Plus, we usually don't have one stack. Well, usual is relative, but in many systems, we don't have one stack. We have many stacks. We have one stack per thread, right? Because if you want a context switch, then you can't really share a stack, because after a context switch, somebody else is going to build up on top of that stack. Context switch back, you'd be overwriting them, or yeah. So we basically have, you know, one stack per thread, and then interrupts can, you know, interrupt whichever stack happens to be currently active. As in, you know, the max interrupt depth has to be added to every stack, or you have to make a dedicated interrupt stack, which lowers interrupt latency. It's a huge can of worms, right? The other advantage to having one stack is you can make it grow into memory that doesn't exist. You make it grow towards the end of your memory. And the processor will get a hard fault, as in an interrupt vectoring to some hard fault handler, whenever you access memory that doesn't exist. So when you do have a stack overflow, you don't just keep overwriting things that are, you know, the root of the next guy's stack, if you will, or global variables or whatever. You don't corrupt things. You stay in a defined state, which basically means you have to like reset and completely reinitialize. But at least you can say in the data sheet what happens, because if you start corrupting other people's data, there is no way to say what happens, right? You have a way of detecting it. If you have multiple stacks, you probably don't have a way of detecting that. Maybe with like a, you know, fancy processor with a memory protection unit and blah, 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 but we don't have that, right? And then there's classic, buffer overflow. Damn clicker. There we go. Okay. Buffer overflow, that's probably the easiest example. Oh, I went off the end, so I need to make the buffer big enough. Well, how big is big enough? Right? We're going to look at some solutions for that, at least attempts, later. But we also have starvation, right? We were looking through out of memory. We have problems where we're servicing, where we're not reacting fast enough, right? If I am an airbag, that's a very sexy not reacting fast enough example because it's it's very easy. Most not reacting fast enough examples are not that sexy. Most of it's about buffer overflow or underflow or violating some protocol. I mean, a lot of bare metal embedded protocols are timing driven, which is not so common in other domains because if you're real time anyway, why not use that, right? So end of package or transfer, master switching back and forth, your turn to send now, my turn to send, is all timing driven. And so if you take too long, you might enter a state in the protocol that you didn't want to enter. You may say, oh, I stopped sending after X amount. Well, we'll consider that a full packet and we'll switch off to you. And the other side of the line, their error handling is probably not that good. I mean, in the introduction to the talk, I wrote, that the utopian views of, the IoT and the Industry 4.0, where everything talks to everything. Well, we don't really know how to do that yet. I mean, I'm not aware of a whole lot of examples where, different devices talk to each other without bugs. Right? I mean, even if you start plugging and unplugging your network cable, you can crash Thunderbird, right? Email client used by a quarter of the world at least, and you can get into a deadlock, right? Which is okay because it probably hardly ever happens, right? It's like not that often the internet connection goes down, and if it freezes, well, you just restart it, right? But that won't work on an assembly line. So you have these dynasties. You have these, you're going to have an assembly line which is made by Siemens or made by somebody else, and wherever there's like somebody else's device which talks to a Siemens device, that's going to be a focus. That's going to cost a lot of money probably. That's going to be a point at which people sue each other when something goes wrong, right? And then, that almost works, but it's mostly just one company, right? And it's mostly like there are industrial data buses that run at less than a hertz, as in less than 1 bit per second, right? I mean, you could attach a lamp to it and watch the data with a pen and paper and figure out what's going through there, right? I mean, you could telegraph faster than this. Because, I mean, why do we tolerate that? Well, because it's pretty damn hard to do, right? It's pretty damn hard to come up with a challenging technology that can challenge Siemens, because you can't just do a little part of it because no one will talk to you, right? And so, I mean, there's business and there's technological hurdles that I don't see being solved all that quickly. And then there's the other example where some kids get an Arduino and make something. And, I don't know, thermostat, actually Heel's here, I think. He woke up freezing quite a few times because somebody thought they should connect his heater to an IoT thing, right? Yeah, that doesn't work. But, we don't have cross-platform libraries that can be on both sides of that connection. We can't, we have entire departments in a lot of companies where you have teams of like 10 people, and their job is to look at the, analyze the timing of the competition's interface so that you can talk to it, right? I spent a lot of my career in the automotive domain with, the vehicle diagnostic port. And we have like a database of hundreds of control units and their timing profiles. And the problem is, it's not like, okay, you do this, and within X milliseconds you have to do that. I mean, X being somewhere down near 2 sometimes, like super fine timing. You don't have a fixed window because the other side is not completely deterministic. So if you answer too early, you could get an answer. It could do what you're expecting 95% of the time, right? So you have like a gray zone, and then maybe darker gray, lighter gray, and then here you have a little tiny patch of white. But you have to look at this a long time before you find that patch of white where you always get an answer. And you have to hit that every time too, right? So basically, figuring that out and knowing all of those timings was where I made most of the money that allowed me to do a bunch of research that I haven't gotten a lot of money for yet. Because what else are you going to do with money, right? So, I mean, the value of the knowledge of those timings is just, it shows how wrong things are running in that industry, right? The other thing that shows how wrong things are running in that industry is that I have, 50 or 100 control units that all talk on the same bus and have different timings. What does that mean? That means that VW developed a protocol stack 50 times, where they could have done it once, right? But this is a problem of abstraction, and yeah. So I mean, they probably did it partly because of mismanagement, right? But there's also very well-managed companies which still do this, which still write a new, a completely new driver every time something changes. And there are people laughing in the back. I assume they have done this. And the reason we have to write a new driver every time something changes is because it's very hard to abstract things in the bare metal field. We'll see why in a couple of slides. So starvation is a problem in hard real-time systems. In a soft real-time system, okay, maybe the user doesn't like you, maybe you're running slow, but it's not a showstopper. But to be late in a hard real-time system means you violated some contract which you're not allowed to violate. And people say, oh, well, yeah, most systems aren't hard real-time. Well, okay. Do you assume an endless RAM? No. Can you stop people from sending you data? No. You are a hard real-time system, right? Do other people expect you to send them data within X amount of time? Yes, you are a hard real-time system. And so, basically every system where there are systems, especially back in the 80s, where a lot of these design patterns were developed. Like, way back before I was born, people came up with ways of doing bare metal embedded development, and they haven't really changed much since then. Debuggers have gotten a bit better. We get more breakpoints. We get a little more traceability. The sort of hardware guys have been doing their job, because that's mostly coming from hardware, right? With software, we get ARM embed or something, which is just a bug farm. So we don't really have methods of even expressing in many states. I mean, one of the things that I have spent some time doing, and I'm glad that some guys from National Instruments have taken up the flag and ran with it, is we don't really have contracts from the standard library about what we can use in embedded or not, right? We don't have contracts about who's sharing what under the hood. We don't really have contracts about RAM use. Almost, many things use the heap. Okay, a lot of times you can use an allocator, but many things use blocks, use atomics under the hood, use things, yeah. I mean, if you have some interrupt service routine, and you're, when you get an interrupt, hey, their new byte came in, I have some FIFO buffer that's, I don't know, 4 bytes deep or something. So within the amount of time it takes to send me 4 bytes, I have to get at least one of them out of there, right? And, you know, again, if this is a clear on read, we've got another problem here, right? If we did an LSIF in the next thing, then it could already be cleared by there, but that's a whole other can of worms. Oops. Okay. So I've got a, you know, some thread, and it wants to, you know, I don't know, change the configuration of the UART, right? Well, it's going to turn the UART off, interrupt off, and then it's going to turn it back on again. Not global interrupts, just the UART interrupt. Okay, so what can happen here? Well, you know, the optimizer could reorder a bunch of stuff into there. Let's assume it doesn't do that, because it probably won't. We could also have another lower priority interrupt us here, which is blocking the higher priority UART interrupt because it's taking up time in a space where it was off. Right? This is, you know, a different twist on classic priority inversion. Right? And we have normal priority inversion as well, where we have a, you know, thread, some other thread. If we have a context switch somewhere in here, then this higher priority thread runs, but it can't take the lock because this guy's already got the lock. I probably shouldn't have called it L1 because that looks like 11. But somebody here takes, tries to take the lock, can't, switches back. We could go into a mid priority thread, and because essentially this high priority thread is high priority, but he's still waiting for this super low priority thread to give the lock back up. And so everybody taking up time in the meantime is going to delay the high priority thread. So yeah, this is you know, the priority inversion problem. So we have this in several other permutations, and since we're a hard real-time system, we essentially can't have this, right? I mean, we could do the hands thing again, like who is sure there can be no priority inversion in their program? Well, yeah, anyone brave? Yeah, I mean, this is, I mean, there is a term for this, which is actually used as sort of a technical term for how we deal with this kind of thing, and it's called the guess and pray method. And that's the truth, right? That the world is built on guess and pray in many, many, many contexts. So yeah, we have, you know, buffer, overrun, underrun. I put that slide in the wrong place apparently. So we also have these sort of missing basic contracts, right? Like if I have a function, I don't know, I have a function a to I, right? Turn a string into a integer. Can that corrupt, I don't know, my heap? Probably not, right? Can I call that an interrupt context? Put it that way. Can I call that an interrupt context? A to I? No. Why? Because A to I relies on locales. Because even though it's an integer, it's not the comma problem. I think it's because some Japanese character set put the numbers somewhere else. Yeah, I mean, you know, what ASCII character is a digit, right? That could be different across different languages. And the locale is obviously, there's just one of them, so it's a shared object. If you have a shared object, you need a lock around it in some way, shape, or form, right? And what happens if you took that lock on the locale, interrupts you, tries to take that lock? Well, it can't get it. It also can't cycle back. It's a deadlock, right? You can have a deadlock on a single-threaded program, right? Because of interrupts. And it takes a while to explain this to people who've never been in this domain. You know, even people on the standard committee are like, what? That? No. Right? Well, okay, yes. And there's this, I guess the technical term is signal semantics, which is kind of the domain you are in when you're not allowed to take locks and whatnot, and so on and so forth. And, you know, interrupt service routines in the Linux kernel, that's actually the best place to find documentation, which again is very embarrassing for us bare metal embedded guys, because we use this a lot more often than Linux kernel guys. And there's a lot more of us than there are Linux kernel guys. But we don't blog, we don't go to conferences, we don't talk about stuff. We just, try and find bugs all day. So, yeah, it's not part of the contract. Like, you don't really have that documentation in the standard library. And there's a proposal now by Ben Craig from National Instruments, who's also giving a talk on another topic at EMBO, which is called freestanding, which basically is the subset of the standard library which you can use everywhere, like also in kernel, also in interrupts, also in everything, which basically means pure functional functions, right? I mean, it's a little different than pure functional because you can have in-out parameters or whatever, but you definitely can't touch any shared state. And you would be absolutely amazed how little from the standard library you can actually do. I mean, essentially, if Stepanov wrote it, it's probably going to work. If not, probably not. I'm not sure if that was what Stepanov was going for, but hats off to him. I mean, most of the, even the Stepanov stuff, like containers, they throw exceptions. Well, exceptions have bookkeeping, that's shared state. We have another problem with exceptions. If you turn on exceptions, you'll probably get an error out of RAM error, because there's a buffer for where an exception goes when you're out of memory, because it can't go on the heap because you're out of that, right? So there's a buffer where that thing lives. And that buffer is, by default, something like, 40K, 100K, which is tiny in sort of desktop terms, but that's bigger than most microcontrollers have RAM, period. So, I cannot turn on exceptions. But on the other hand, turning off exceptions is still technically undefined behavior. Okay. So yeah, the year before last at CPPCon, the grill the committee session, somebody said, "Oh, why don't bare metal people use C++?" And the committee was basically said in a million words, "It's a marketing problem." That's not true in my mind. It's not just a marketing problem. As on a processor with less than something like 40K of RAM, you cannot use C++ correctly, period. When you turn off interrupts, nothing's going to go wrong. The games guys do it all the time. But, throwing an interrupt at that point is...
Exception.
Throwing an exception, yeah, sorry, damn. Keep corruption somehow. Or global, anyway. So yeah, throwing an exception is undefined behavior. And if you kind of go dig into undefined behavior and look at sort of how Clang is starting to aggressively optimize around undefined behavior, that probably is not going to end well, right? So we could probably make exceptions work if we did a better sort of quality of implementation kind of thing, right? We could make a version of the standard library which, you're not required to throw a text string with your exception, right? You could you could make a standard exception have no description. That's still standard compliant, right? So you could make that buffer, 20 bytes or 10 bytes or something like that, if you really squeezed it. But nobody really invests in that kind of thing, I guess, because most embedded companies don't earn their money with software alone, and usually don't understand sort of the tech debt issues that we have in software. The fact that we don't have a standard library that we can use in our domain is tech debt, right? The fact that we're using C is, in my opinion, tech debt, right? There are so many different things where you can shoot yourself in the foot. All of these things I've brought up so far are problems both in C and C++, except for the exceptions. And as far as I know, I don't really have any good solutions on how to solve that in C. I will be presenting some solutions of how to solve that in C++ shortly. So yeah, I've been pushing, and a few other people have been pushing for more contracts from the standard library, but I don't think you're ever going to get any from Boost. Right? Like, I had a very funny episode where somebody wanted to use Boost to upper, because Boost to upper is the most upvoted Stack Overflow answer of how to make a string uppercase. And yeah, they were getting a very weird linker error, and they reduced the program down to 1 to upper in main. That was it. And linker error that they'd never seen before. And what the linker error was? I'm out of flash and RAM. And it was not a very small chip, because Boost to upper pulls in locales. Locale has a lock around it, pulls in multi-threading. Locales, also pulls in date time somehow, because date time has to do with locales, right? I mean, you essentially pull in all of libc, and well, not quite, but almost, right? Like, I mean, there's some error message in there somewhere that uses printf, so you pull in all of printf, like all the 50 different variations, because I mean, the format string in printf it's not runtime most of the time, but it's not in a way that the optimizer understands it. So you essentially have to pull in the entire library as soon as you use any of it, right? Because C is efficient, air quotes, right? I mean, you pull in, essentially every program that has any printf in it will have the format string for %z. Who knows what %z is? Size t. One guy knows this, probably because of some other C++ trivia, right? Have you ever used %z? Yes. Yes. Oh, wow. Not worthy. No. Yeah, no, but you don't need that in your program if you're not hip. But it's there because we don't have this. We can't express ourselves to the compiler and as pure a form or as an understandable form in C as we can in C++. Right? In C++, we didn't need. We'd have some combinational template thing that would only pull in what we need. Some compile time format string, who knows? So basically, the world is built on sand. If you're using C, that's your problem. If you're using C++, it's C++'s problem, right? It still doesn't make it better. So we want, what are these guarantees, right? One that I haven't talked about yet is a forward progress guarantee. I mean, at least I touched on it with the interrupt example, but we have a different forward progress guarantee, which is why that little asterisk is there. I mean, most programs, forward progress guarantee means you're probably going to finish at some point, right? That's very hard to prove. Most programs don't even attempt to prove that, right? On bare metal, we want a different program. We want to say, okay, if everything goes wrong, if every lock we encounter is locked forever, right? If every if every compare and swap operation or whatever, I mean, there are some atomic operations where theoretically nobody can get it in some cases. Those always go wrong, right? Everything always goes wrong. Do we still complete? That's the guarantee that we need to make. We also want to be, deterministic or, within a certain amount of time. I mean, we are hard real time at the end of the day. And it's not just about fulfilling hard real time guarantees. Being deterministic also means that you are in less different states because time plays less of a role. So bugs that you see, you will either see more often, which is probably good because you see it yourself, or much less often. I mean, it pushes things in both directions. And if less often means there's a probability no one will ever see it, that's probably good. If it's more often, that's probably much better because you're going to see it and test it. Those sort of windows in time where I have sort of these gray zones at both edges and some tiny little white window where I always get an answer. If those were very deterministic systems, then there would be less gray, right? Heap allocation, for example, is a very non-deterministic thing because how long that takes depends on everything that happened since startup, right? You change one thing, maybe something gets put in a different place, then yeah. And so that's also impossible to test, right? You cannot predict the shortest amount of time or the longest amount of time it will take. Well, I guess you can predict the shortest amount of time, but you can't predict the longest amount of time it will take to get something that you allocate. You'd actually for malloc to return. Which is a problem, because you can't do it when you're holding a lock, you can't do it in an interrupt service routine, you can't do it anywhere except for the very lowest priority thread, which is probably useless. RAM use I went into, another good example about not having contracts or guarantees. If you're using standard function, right? Standard function has a small object optimization, meaning if you put a lambda in there or a function pointer in there or anything in there that's smaller than the size of 3 pointers on that platform, then all of the standard libraries agree that that thing was not going onto the heap. It's not guaranteed, however. It just happens to be the size of 3 pointers, right? So, I mean, even in other domains, if you have a massively parallel program and you're using standard function all over the place, but you're always using it with small objects, and you change standard libraries, and this standard library says, hey, I want 2 pointers. And all that's suddenly going to the heap. And your program probably slows down to the point where it's unusable. So yeah, that's not part of the contract. Right? It would also be cool to make it bigger in some cases. But anyway, so yeah, I mean, it's hard to give enough guarantees anywhere, right? And again, if you look at the standard library, the part that really gives you a lot of guarantees, even if they're not enough, is the part that Stepanov wrote, right? I mean, we're kind of digressing as sort of a discipline here, at least in that sense. So yeah, the problem with RAM use is once you start to constrain yourself in that regard, it makes it harder to upgrade things. So yeah, this is a hard problem, but it's definitely not documented. And the other thing that's one of my personal pet peeves is stack depth, because this is something that you would probably like to know about functions you're calling, but the author cannot tell you, because it depends on what the optimization is. I mean, basically, you don't care what stack depth is in debug mode. You want to know what stack depth is in release mode. And the library author can't tell you that. So how do we solve that problem? Right, that's kind of a tough one. So kind of going through sort of how we start to deal with some of these problems. If we go all the way back to out of memory, common practices. I'm gonna have to keep moving around so everybody gets at least a chance to see the. Yeah. We kind of assume, well, I'm gonna look how deep is the stack. What's sort of the what's the high water mark, right? How high does the stack ever go? And then I'm going to use like the patented, the same way my grandfather did it or whatever, and say twice as much. That's the magic amount. That will never overflow. And that's obviously not true. It may be true. I mean, there may even be a pretty big chance that it's true, depending on what you tested and whether you actually found the long, deepest stack path, and whether your interrupts aligned, if the stars aligned perfectly so that they interrupted each other in the right pattern. There's also a pretty good chance that it's not true, that it can actually grow further than that. Right? And again, you can't code review to figure this out. It's after optimization, right? Even if you try to code review your optimized build, you're going to make mistakes, right? Like, I don't know, is there anybody feeling comfortable they could do this on a reasonably sized program? I mean, yeah, I'm not expecting to see hands, right? So yeah, our method of dealing with this is inherently flawed, in my opinion. We are fighting windmills, right? So we're, in some sense, we share something with my hippie past. We are fighting things for the wrong reasons and without any chance of ever winning, right? I already mentioned that we're, hard real time. Another reason you can't really use the heap is you can't lock around it, right? So, I mean, there are these incredibly, I guess we could say people that are feeling very lucky, who have made a embedded version of libc. It's called New Lib Nano. And New Lib Nano is made specially for us bare metal embedded guys, where they stripped out everything we're not going to use. There's still a heap in there, and this heap, there's some note that we shouldn't use it in multi-threaded programs. The reason for that is, the lock and unlock callbacks around the heap, those are no-ops, right? They don't tell you that. They tell you to not use it in a multi-threaded context. So we have a single-threaded program that happens to have interrupts. And we can corrupt our heap, right? There's a relatively low chance of that happening, but we can. Right? There's another sort of pet peeve of mine that probably doesn't happen too often in practice, but as of C++11, function statics, as a static variable inside a function, they are guaranteed to be initialized once. Right? In other words, there's some kind of locking mechanism where when the initialization has started, no one else can initialize that until it's finished, in which case they get the initialized version. Right? They're not thread synchronized as such, but if you have a function static that is const, essentially you are guaranteed that everyone will see the finished state of that thing. Right? How do we implement that on a microcontroller? Or anywhere where you have interrupt service routines? You could maybe implement it by turning off interrupts. However, I don't think there is a way to document that well enough without people still shooting themselves in the foot. You pay twice as much for a chip if it has 10% faster interrupt service routines, right? This is something we're actually using, right? This low interrupt latency. For the language to just circumvent that's not an option. So essentially, my advice is, in this domain, don't use that. You just cannot use that C++ language feature in our domain, unless you can guarantee that that function will never be called from an interrupt service routine, in which case, the problem is documentation also builds on programmer discipline. And as I mentioned earlier, I'm convinced programmer discipline is a myth. It's one of those unicorn things where you see things that are very similar to a unicorn, they just don't have a horn or anything. But you never actually see we get close, but if you document that, how can you be sure that people will read that documentation? Right? There's some function out there that calls some other function, that calls some other function, that calls some other function. Somebody code reviewed all that, made sure, okay, I can call this from an interrupt service routine. And someone else came along and said, oh, look at this function, I can add a function static here, right? That way around, where somebody wrote the call and somebody else changed the implementation, that's pretty impossible to document, right? It essentially means whenever you want to add something like that, you have to do a full code review. If you want to call something from an interrupt service routine, you have to do a full code review, right? If you want to do anything, you have to do a full code review. And we don't do that, duh, right? We never get anything done. So, yeah, that's another unimplementable feature in C++. So, I started out all gung-ho, C's a barbaric language, we should stop using that and whatever. I really should have put that graphic in here. There's a really, really funny comic with some aliens coming down and, some cavemen, and the aliens say, stop using C, and the cavemen throw a spear, and if the aliens fly off and nobody understood them, right? So I'm kind of coming around. If you don't use the actual advantages of C++, if you use C++ as C++ in 21 days C++, as in, C++ 98 without the standard library. And as we established earlier, you can't really use the standard library, at least most of it. So what does it really buy you? It buys you function overloading. Well, that's about it, right? Okay, maybe const expr is pretty cool. So function overloading and const expr. And it drags in a whole lot of stuff that will bite you and nobody will tell you, right? At least it's not really common knowledge, because people who have had bad experiences with it have just gone back to C and said C++ sucks, and not getting really specific because, oh, you didn't use signal semantics in that context. And yeah, like C guys are not going to learn standardese to tell us why they don't like our language. Yeah, so I'm kind of coming around as that sort of a pragmatic. Looking in the future, I really hope we're not programming in C in any sort of large scale in 5 years, whatever. So what we need to do is we need to actually make the advantages of C++ viable or usable in the embedded domain, because the power of C++ is its ability to abstract things, its libraries, right? Because with C, I have basically portable assembler, right? I have a bunch of commands that I can compose with each other that are all essentially a strategy pattern with a code generator connected to the back end of it, right? So I have a switch statement, that's strategy pattern code generator for this processor, strategy pattern code generator that for, okay. So I have some set of commands that I can compose. In C++, I can make my own, right? C++, I not only have composable pieces that have like a swap-outable code generator, I can build my own code generator, right? I have a Turing-complete language within the language with which I can write libraries, right? I can put rules in. I can generate code essentially in any way I want to. This is what I took away from Alex Andreescu's book, and then I went and tried it, and it was like, oh, so you can do like lists of 20 things, and then the compiler crashes. Well, that doesn't seem all that Turing complete. And so, yeah, that's actually where me and Heel and a bunch of other people spent a lot of our time over the last couple of years, increasing what we can do with temporal metaprogramming. And compared to Boost MPL, which was the gold standard up until C++ 11, we've increased the speed and the size of metaprograms you can write by about 3 orders of magnitude, right? You can write 1,000 times more complex temporal metaprograms now than you could back then. Okay? So we can do a lot more stuff, and it's gotten somewhat easier too, but we're still playing with that. So we should start using this, because I was talking about heap alternatives. Well, essentially, if you think about it right, maybe you got to be in the right mindset. Maybe you have to be really drunk at a bar, or I don't know. If you think about your program in the right way, your program is a very, very complex state machine, right? And if you look at any piece of data that would otherwise go on the heap, that piece of data is either going on the heap because its size is known at runtime, in which case you're thinking about high water mark or whatever, however you decide what its maximum size is, because it can't be bigger than your heap, right? So you must have some notion of some upper bounds of how big that thing can be. And as soon as you cannot prove that your worst case scenario does not have thing A at max size and thing B at max size, they can't share. So, on our microcontrollers, we can't say, oh, well, if we're not using the RAM, then somebody else can use it. There is no somebody else, right? Nobody cares if our RAM is full or 10% full, as long as it's never overflows, right? So variable buffer sizes are hard. The pragmatic approach is probably figure out whatever the maximum is and make that a global variable. You're paying for it, but if you cannot prove that you are not paying for it in the otherwise maxed out memory scenario, then you are paying for it anyway, plus heap fragmentation, plus bookkeeping of the heap, and so on and so forth. Because the only thing that is important is the high watermark. Everything else, who cares, right? If you can prove that, a good example is a digital camera, right? Either I need a USB stack and a packet pool and that kind of stuff because I'm connected to a computer, or I need a pixel buffer. I never need those two things at the same time because either I'm taking pictures or it's connected to the computer, right? I mean, camera won't even let you do both at the same time. Probably because they're actually reusing the RAM, right? So if I think about sort of my camera state machine, then I have, something like this, right? I have global variables, global variables over here. I can think about as sort of my base state that I'm always in, state local storage in my base state. And then I have, some state over here that could be, I don't know, DM, who cares? That's, I don't know, maybe that, your ISO settings or something. Has nothing to do with USB or pixel buffer. Although I guess you could argue that it doesn't need to be there in USB mode. I don't care. I guess no, that state should persist past a USB plug unplug, right? So this has nothing to do with it. So it's an orthogonal region, right? So we have D over here somewhere in memory. Well, why do we have a gap, right? Well, we have a gap because we could swap out A with, with B and C, because C is a substate of B, right? So I essentially have two orthogonal regions. I look for, in each region, the largest state or combination of states which is reachable in this region, and then I lay out my memory like that, one orthogonal region after another. This way I have zero bookkeeping overhead, I have absolutely deterministic behavior. I can tell statically at compile time if I can overflow, right? I have gotten rid of the heap and maintained the functionality of the heap, right? And I can switch to another state. Well, I'm using even less. Still works, obviously, right? So at least in theory, if you model your program as a state machine, then you can profit from the fact that not all of your objects will be active at the same time, which is the whole reason why you use the heap in the first place. That's essentially the only reason you would ever use the heap. Otherwise, make them all globals. Global optional. Maybe it's there, maybe it's not. And yeah, the only reason the heap exists as a thing is because not all your objects are active at the same time, right? The one caveat could be maybe I have like a pool of objects, so I have many of this kind of object or whatever. Well, put that pool in state local storage. When can that pool exist? Oh, it's packets on the CAN bus? Well, only when I'm connected over the CAN bus, right? I'm not in that state. That pool can be used for whatever else. So yeah, state local storage, greatest thing since, well, it's even greater than state sliced bread. I'm not sure if that joke is actually even going to work across the language barrier of not being like, yeah, anyway. The dynamic buffer problem is actually somewhat solvable. Most dynamic buffers are dynamic because user input can be different sizes, right? You think about, I don't know, you're part of some RESTful API. This is another thing where I just get really mad when people start talking about how far we've gotten in IoT and Industry 4.0 and so on and so forth. Well, yes, we have systems that run off of a battery for 10 years. We have systems that can do this and that and whatever. We can talk to each other over JSON and RESTful appers and MQTT and all these protocols, right? This works as long as you don't try and prove that it will always work. Because JSON, at least as far as the standard goes, is built on UTF-8 Unicode. UTF-8 Unicode, if you actually want to handle that correctly, And the only library that comes close is the ICU library, which compiles down to like megabytes of data, of program code, right? That's not going to fit on a microcontroller, right? So the system, I mean, you know, people get creative. Oh, well, processors are going down in price. Well, maybe you can get a processor that fits your budget, which will fit the ICU library. But it will, I'm very, very, very sure that that thing will not run 10 years on a battery, right? Because RAM costs energy. It's not just a price question. It's also a question of energy. And having more RAM will cost you more energy. So yeah, it's not solved, right? I mean, the reason it usually works, you know, emphasis on usually, is because we don't use emoji in our MQTT JSON-based packet protocols, right? We don't have the unicorn field or the poop field or whatever you can do as far as emoji goes, right? We don't use Chinese characters either. But we theoretically could, right? I mean, you know, we're trying to build stuff on strong foundations, not on probabilities, right? I mean, there's a really great joke where you say, okay, what's the probability of this going wrong? Well, we had a 99.99% of it going right. Well, what's the probability of that thing going wrong? If you multiply enough of those together, you eventually come to a probability of it working of 0, right? At least if you have infinite things, right? We want to build on, you know, stone or whatever you want to use as a metaphor, the same way Stepanov built a lot of the early standard template library. I mean, he made mistakes, we're going to make mistakes, but at least we're going to try, right? And which basically means we have to go all the way back to libc. I mean, libc is very, you know, well, it's as old as I am. It's older than I am. And so, you know, back then they made assumptions that the, you know, that everything's single-threaded, which led to things like error no. That compilers can't use templates or optimize things or whatever, right? Which led to printf. You know, that being generic only went through the data route, right? You couldn't be generic in a sort of template sense, as in a compile time generic, compile time polymorphic, compile time composable kind of a way. That just wasn't known at the time, right? So the other problem was they had the same, well, they have the same distribution problem that C++ still has today. I mean, if you want something to be usable by everyone easily, it's got to go in the standard library. And that, in my opinion, is absolutely stupid. Because, you know, there are discussions of, well, we really need this thing, and we should put it in the standard library. I'm like, okay, you haven't even built it yet. And you think it's going to be bug-free when you specify, like the specification is going to be the right one when you put it in the standard library with no, I mean, core language stuff, okay, they got to do that, right? You can't have a boost of core language, right? But essentially, boost is awesome. It's just old, right? I mean, there's not a whole lot happening in boost anymore. Because again, boost is one giant monolithic thing. If you want boost, you probably got to pull all of boost and compile all of boost. Problem again, right? I mean, I'm weird, so I did assembler, no package manager for assembler, C++, no package manager for C++, and then, you know, after I mastered templates and whatever, I did Python program. And I went, wow, this is super easy. Why the hell don't we have this? Right? So, I mean, I think one of the most important projects currently for C++ is package managers. And finding ways of putting our, I mean, because we're a little harder than other languages. I mean, you know, cross-platform Python is a whole lot easier than cross-platform C++. Right? So we have platform-dependent stuff. We have to be able to express that within a package manager. We also have to have our package managers work cross-platform. So they got to work on, you know, both Linux and Windows for idiots like me, right? So, yeah. Coming back to libc, they put everything in libc. I mean, why are locales in libc? Libc, I mean, its sole purpose should be to bridge system to user space, right? If you want to, you know, hold a lock and you don't know how to lock on that system, there should be a syscall going through libc, which gives you an os lock, right? You want a file handle, libc. You want, right? But locales, that's something that's continuously changing, right? Like German recently made an uppercase version of their like SZ B character thingy, right? That's going to break every libc out there. Why is that not in some user-based library? That is absolutely stupid. So if we don't have a kernel space, why do we need libc anyway? Right? Well, they put some other stuff in libc, which again, I don't think should be in there. Global objects are initialized by, you know, on entry or whatever it's called in libc. So we need that. What else do we need? Well, at exit. Well, we don't exit on microcontrollers, right? Like we run until somebody pulls the power out. And not having an at exit, that's probably a good thing, because you probably don't want to be relying on anything that calls at exit, because that's never going to get called. Right? So that's kind of where we have to go back to and then build up everything again. I mean, it's kind of like the laws of physics. If you were to change the laws of physics, the world would still work. It would just be very, very different, right? I mean, we probably wouldn't be here, but it would still work in some sense. So if you look at things like the heap, well, we can't reason about the heap. Let's not do that, right? Let's just not have a heap. Let's do it with state local storage and pools and whatnot, right? We can't deal with shared state. Well, let's not have shared state, right? Let's do message passing. Let's do, I mean, on the state that we have to share, let's make that atomic with, you know, compare and swap or whatever, right? We have problems with max stat depth. Well, that's got to be a tool, because we cannot do that as humans, right? That's just not possible. Either we leave a lot of performance on the table and not optimize our code, or we do it wrong, or we make a tool that does it for us. Well, how hard is it to make a tool that does it for us? Well, that really depends on how you code, right? I mean, if you're allowed to do everything, like virtual function calls and just general indirect function calls and recursive function calls and things like that, well, that's, I mean, I'm not sure if somebody's even proven that to be NP complete, right? Like, that's a hard problem that no one's solved, and I don't expect to be solved anytime soon. Because you need data to know where that branch is going, right? Or whether that recursive function call will end. But if we change the laws of physics, we say, okay, you can't do that, right? I mean, some people are like, oh, okay, you can't write code anymore if you can't do that. And that's almost true. Because if you try and write code the way we've been writing code for my lifetime, then that's pretty hard, because we're used to dividing code up into different compilation units, right? We don't know. I mean, if we have a function pointer, we don't know all the functions that that pointer can connect it to. Otherwise, we could just make a variant of function pointers, right? It's going to be one of those. It's going to be A, B, C, D, E, F. One of those is going to be in there. We know where it's going to go, right? At that point, even though it is dynamic, a tool could just follow all of those paths and figure out which one has the deepest stack, right? But we're used to using the linker to patch together our program at the very last step, because back in the day, you had to do that, right? You could not have a program all in one compilation unit. And anymore, there's this thing called a unity build, where you basically take one CPP file. That CPP file includes all the other CPP files, and you just compile that one file, right? You eventually made one translation unit out of your entire program. And the funny thing is, that works. Like, compilers and build machines are, I mean, I heard a story about somebody who I believe who made a Unity build out of GCC because he wanted to compare how good the link time optimization is compared to normal optimization. Turned out it's pretty much the same thing, and it turned out it used 200 gigs of RAM, but he happened to work at a company where you could use 200 gigs of RAM to compile something. Right? I'm jealous. But and we think about sort of the difference between the size of program. You can't run GCC on a microcontroller, right? You have some upper bounds of how big your program can ever get, right? And I mean, just sort of as a rough estimate, you have about 1 million times more RAM on your build PC than you do on your microcontroller, right? And so it's probably always going to work because 1 million is a big number, right? 1 million. We'll do a pinky for the million. So we could theoretically write programs in this domain that are all Unity builds, which means we don't have to rely on the linker to connect stuff for us, which means we can use variants, templates, whatnot. We don't have problems with the one definition rule anymore, which is one of the hardest things to teach people to use templates, is to never violate the one definition. If you only have one translation, you have one definition, period, right? I mean, you could theoretically have a problem with like too early instantiation, but that usually results in a compiler error. So at least they go find somebody who understands it, right? Rather than it silently failing. So these are sort of, yeah, different laws of physics. At this point, we can write programs which don't have any dynamic calls. At which point, I think one of Warner's students wrote a script that just looks at Clang intermediate code and says, okay, this is your max stat depth. There you go, right? Can be enforced by tools every time you build, costs nothing. Yeah, it becomes a trivial problem. And so we don't have to guess and pray again about max step depth, right? We also can at least start to think about tool analyzation of min-max execution time, because that was the other thing you can't figure out through a code review, right? Loops kind of get tricky because you don't, I mean, it's usually data decides how many times you can go through the loop. But on the other hand, you don't do a lot of looping in an interrupt service routine, right? Like the very high priority stuff, that's probably not going to loop anyway. So at least you're closer to a solution there. Right? And, you know, coming back to, from this giant sidetrack, I didn't put in as many slides as I wanted to make the talk longer, so you're going to have to forgive me for a couple of missing slides. This talk is going to be held at EMBO in a slightly more refined form in an hour. On the other hand, most of the stuff I've been talking about will be in somebody else's full-length talk that goes before mine, so I can just point. Coming back to the problem of big buffers, we can use this awesome power that we have in C++ to essentially define, I mean, you know on a microcontroller what the JSON packets are that you're going to be accepting, right? You don't just accept any JSON packet, right? So we should be able to, I mean, this is pseudocode, right? I just wrote this up there as kind of an example of how one could do this kind of thing, right? You have a user-defined literal, takes a string, that string goes into a template monster. Template monster builds us an automata, like a, you know, same thing you get when you build a regex thing, except it's compile time built. It's, you know, for all intents and purposes, a tiny state machine that will, you know, throw away everything it tells it sees an angle bracket, right? Throw out everything that's a white space. And then as soon as it sees first letter here, if it's not an N, if it's not an A, it will throw away everything until it sees a comma, right? Because in JSON you can have extra fields, right? So essentially, any RESTful microcontroller that accepts JSON packets, as soon as you no longer assume endless RAM, you are violating JSON, or, you know, the RESTful protocol. Because adding extra fields that somebody who does not support them will ignore is just part of the deal. If I add 10 gigabytes of extra fields, there's no way you're supporting that, except with this thing, because it doesn't save the state and then go through. It processes this byte by byte, right? I mean, once it gets to here, say, then it's got to start saving a string. because the user wants that string. We have theoretical overflow potential. If it's an int, then we don't. Right? If our RESTful API is built entirely out of bounded strings, where we define how big they can be, and numbers, then this thing will essentially, when it's finished, call the lambda with a tuple of either name and age or ID and temperature, whatever the user put in those fields, right? In C++17, we could do an if const expr, decide which one it is, handle that, we're all good, right? So this thing will need enough state to save both data fields and some buffer. Like you could iteratively build up a uint32. You probably want to save that many characters as a buffer somewhere, and then do the conversion when you have all of the characters, right? Yes.
Can I interrupt?
Yes.
I think it's good to have a little break now.
Oh,
Something
yes,
to drink?
sure. Very good. Yes. Beer. Beer is always good. I haven't touched mine. Good thing I'm not in Germany. I would have been hung by now. Dutch are very tolerant. Okay, picking up where we left off, compile time generated automata to do whatever you want, including parse JSON. I actually kind of lied to you because this syntax is not valid C++ now. It will compile, like you could make a backend library to do that, which will compile in GCC and Clang. It's like a the compiler extension that does work, and it's been proposed once by Louis Dion as a part of the language, because it builds on the fact that you can make a user-defined literal which takes a string, and you get that string as a variadic pack of char template parameters rather than a string. And it's a little complicated why you need that in order to do this effectively, but you do. So the first time it was rejected because I guess most people didn't understand the use case. But in the meantime, there was a talk by Hanna Dusikova, which I'm probably butchering, but it's actually not the reason Louis named his library Hanna. It's a coincidence that the best metaprogramming girl on the planet is named Hanna, but she implemented a compile time regex automata generator thing where you can just say this underscore regex, and it builds you a regex matcher at compile time, which is about 300x faster in many examples than the runtime built one we have in the standard library. So this is what regex should have been. And the amazing thing is, she told the world that she did this at CPPCon on a lightning talk last year. She wrote it 3 years ago. So we could have had this. I mean, that was not that much after standard regex got standardized, right? Like, if she had been part of the standardization process, we may have gotten a better regex. But with, armed with this new use case, I think they will probably be able to convince the standard committee that this is a good thing in C++, in which case we can build all sorts of automata from domain-specific languages in text form now. Yes, I very much, if you're like a template meta nerd, check out her GitHub repository. She has a style that no one else has, as in she taught herself, apparently. And it is mind-bending and very interesting. So, ticking off this list, we have, the reviewing the problems again of starvation. Disabling interrupts means essentially full code review every time you change anything, because you may be violating some of your latency guarantees. How do we solve that in a definitive way? Well, we just never disable interrupts. We always use lock-free structures. And that actually is not as hard as it sounds, because we have much more powerful compare and swaps on microcontrollers, right? I mean, on modern processors, we have speculative branches, we have processors which are very far apart from each other, where one will have done several instruction cycles before the signal even gets there, blah, 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 blah. Microcontroller, we have one processor. The only reason this is interesting to begin with is because of interrupts. And we have, you know, a compare and swap kind of a thing that basically says, hey, was I interrupted? If yes, then, you know, compare false and do it again. If I wasn't interrupted, well, then everything works. So you don't have ADA problem. You can block over multiple things. You can do a whole lot more powerful, a whole lot more easy atomic stuff on at least ARM Cortex microcontrollers and many others than you can on big machines. Nobody's really done the legwork to build these kinds of queues. We got a guy that's kind of starting to work on this now. Definitely works in theory. You know, we have the problem with interrupts that we can't just use locking anyway, because we could deadlock. We do need, you know, preemption, as in I'm going to interrupt you for two reasons. For one, because we can get low latency, we can get guaranteed low latency. We can also share a stack, because the most efficient way to do things is to have one stack, right? Because then, you know, if everything on this stack runs to completion, which again is kind of changing laws of physics, because then you can never wait, you can never sleep, you can never block, because you have to run to completion. But assuming that's possible, and we'll get into sort of how that's possible, if everything runs to completion, you essentially do task switching, as in you finish this thing and go on to that thing at a defined point, right? So when you're done, when you would otherwise block or otherwise sleep or otherwise like finish, you have an explicit place where you store your state in state local storage or global variables or wherever you want to store it. You don't have all of the implicit state that is in your stack, right? When you do a task switch, you need to save the whole stack, because there might be something in there you're still using. Plus, you have to know where to return to, right? But if you only switch tasks, in air quotes, when you're all the way down back at the bottom of the stack, then suddenly your max stack is not sum of the max stacks of all of your different tasks. It's max of the max stack, the depth of all of your distant tasks, which is way less RAM, typically, right? It also means that latency gets somewhat predictable, because we can make rules of what can preempt what, right? We can put things at different priority levels. And if we never turn off interrupts, we can prove, at least for the highest priority, what its max latency is. But if we also have, I mean, we do need external constraints of how often this highest priority interrupt can happen. I mean, if it can just happen again and again and again and again, we can starve everything forever, right? But that's probably not the case, right? If it's a button, we probably have some debouncing circuitry on there, which will take a while before you can press it again. You know, a while is relative, you know, probably smaller dead time than you could ever press yourself. If it's data coming in over a serial port, well, the baud rate gives you a ceiling of, a floor, if you will, of the duration between two interrupts, right? It can't be less than it takes to send 9 bits or whatever your, you know, start and stop bit scenario is over that wire, right? So if we define these sort of external constraints of how often interrupts can fire, and we know how long the interrupt can take, we can start making guarantees about the next priority level, right? And on down the chain. I mean, if you go down far enough, that gets pretty hairy, but usually there are only a few interrupts which are critical enough that you really need to prove them, right? So we can actually start to prove these things not through programmer discipline, but through tooling, which is much more reliable than programmer discipline. Oh, I already said that. Okay, so to solve this, we can make hardware interactions default, which is a talk I have yet to give, sadly. It was not accepted at about 6 or 7 conferences. I'm not sure if I'm pitching it wrong or what the deal is. The user can opt out of Atomic by default if they promise that they are not going to access that special function register from different interrupt priorities. Then we can make it as efficient as possible because we don't need to make it atomic. But it's better to have it on by default and opt out, because then you have to read the documentation to do the unsafe thing, right? Usually it's the other way around. Between priorities, we probably want to do sort of more of a message passing, right? And that's the way pretty much the whole industry's going, is not share things, pass messages, but it works pretty well for us too. You can make a single consumer multiple producer queue pretty easily, atomic queue, pretty easy, and that's basically the structure that you need. You have everything above the lowest priority can push into this queue. You can hijack unused interrupts to essentially preempt the lowest priority whenever something happens. I know you're in a high priority. You don't want to do it in your interrupt because you don't want to starve the next tier down, but you do want it to happen before the lowest priority interrupt gets back. Well, there's going to be some interrupt you're not using. You hijack its interrupt service routine, set it explicitly. The interrupts in the priority range in between will get serviced, and then when you get down to that priority level, that will fire before you get all the way down to the main. So rather than having a priority queue, you essentially have multiple queues, one for each priority, and then empty them from highest priority to lowest. We do have other problems. We're taking most of the problems of the domain off of the table here. We're adding other problems like sequential consistency. That can be a problem because, a higher priority can pass up a lower priority, and that may not be what you want. Usually it is, right? So, yeah, we are introducing some, but they're usually a lot easier to solve. If we want to make something atomic, we have shared state between different priority levels, and this shared state is larger than one compare and swap operation. Then it is somewhat hard to do atomically, but again, we command our entire system. We know how many interrupt priorities can access this thing. We can essentially make, for the sake of argument, 3 shadows. Everybody updates their shadow, and the pointer to which shadow register is currently active is a compare and swap operation, right? So we can make bigger things still compare and swap, paying a little bit of RAM. But we still don't have to turn off interrupts. So as soon as we want to run to completion, as soon as we don't want to be using threads, we're essentially using an event-based paradigm or a reactive system, or there's a bunch of different buzzwords for essentially the same thing. Whenever something happens, I have a handler that runs. When that handler's done running, I go back to the event queue and say, what's the next thing? What's the next thing? What's the next thing? Right? Probably the most commonly known example of this kind of thing is in the C++ world is GUI programming with Qt or something, where events come in. You essentially have like this big composable event filter mechanism, which are widgets, and you handle events all day, right? Probably the most commonly known in Softrall generally is Node.js, and the complexity of programming in a sort of callback to callback manner rather than a thread where you sleep rather than callback, right? So rather than do this, then sleep, do that, then sleep, do that, then sleep, you would take those 3 pieces, put each of them in a callback, and have them happen wherever the thing you were waiting for in your sleep happens, right? That's kind of a hard model to think in. And it can't be as hard as people pretend it is, because JavaScript programmers do it. And yeah, if they can do it, I mean, a lot of these guys are casual programmers. They're graphic designers by profession or something and can program in this model. But that has gotten, I should be, okay, yeah, I said all that in the wrong order. Anyway, that has gotten a lot easier because of coroutines, right? A coroutine is essentially, a lot of people don't think about them this way, but I think about this in this way. It's essentially a state machine with a bunch of event handlers and a sort of public interface with which you can express chains of events as thing, co-await, yield, whatever. You can build state machines that have mostly the structure of go to the next thing, 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 in a more thread-like way, right? So, I mean, how are coroutines implemented under the hood? Well, there's some index which says, okay, where am I in this coroutine, right? Because if you call back into it and you're at the third co-await down, you're no longer at the beginning. So the entry point's different, right? So you have kind of your state variable, and then you have all of the local variables that you are using in different parts of the coroutine. Those cannot go on the stack because the coroutine returns when it gets to a co-await, right? Or a co-yield, or yeah. It will return and go back down the stack, right? And those things have to live until the next portion of this coroutine is called. They have to still be available. So you have this coroutine local storage, or whatever you want to call it. In some models, that goes on the heap. In sort of the Gore coroutines, that goes in some magic storage. That's kind of part of the coroutine object, if you will. But Gore coroutines are essentially a library implementation behind keywords presented to you by the language, right? Which is actually much the way that exceptions are implemented, right? You have keywords in the language, they call some function in a library, you can decide what that does. Same thing with, co-await. Essentially a keyword, and you can decide what that does. And so I am convinced, we actually have not done a proof of concept of this yet, but I am convinced that you could make the coroutine local storage state local storage in the state where this coroutine is a handler, and then once you reach a point in this coroutine where it would otherwise exit, you would do a state change to whatever other state where you have another coroutine and another state local storage. So even though your whole program is essentially one very large state machine with many, many, many handlers that kind of bounce around between different states depending on which events you get, many orthogonal regions in one state machine, you don't have to program it that way or think about it that way, because you can put a lot of that in coroutines and program much the same way as you would normally. Right? Rather than sleep, you just do co-await. Or sorry, rather than a blocking call, you do co-await. Rather than sleep, you do co-yield. Right? So, yeah, I mean, we can make a framework that you can pass drivers or your own objects to with some interface, which is yet to be fully defined, but will definitely include a startup portion with compile time readable commands of what's going to happen at startup, with which interrupts interest me, what interrupts do I want to handle as an object, right? If I'm a UART driver, I'm going to say, hey, I want on UART interrupt to be me, and if the user wants to use a DMA, then I need that interrupt handler too, right? I may even be one of many things that want that interrupt handler, and I may be sharing some DMA multiplexing object, if you will, right? Which will delegate to whoever owns that DMA at that point in time, right? So, I mean, if you're familiar with a lot of my other talks, you may be noticing sort of a pattern here, right? Like my last big talk at CPPCon was about how to make compile time composable objects, right? How to put things together in a way that there are no dynamic calls, right? We can use that to essentially compose our entire program into one giant event filtering thing, much the same way we do in Qt, but it's not going on the stack and it's not a bunch of virtual callers. It's all static dispatch to whatever's there. Within this giant event filter thing, there will be state machines at some point because the events are going to a different thing depending on which state we're in, right? There are interrupt service routines which are statically bound because we know what interrupt service routines which object is interested in. The framework will just put that vector there, right? In the interrupt service routine vector. Basically, it's just a big array. And you tell the microcontroller where that array is. In a different offsets in that array, there's the function pointers that get called when an interrupt happens. And this is another thing where my hair stands on end when people say, oh, C is the more efficient language, right? Well, go look at C frameworks, right? And how interrupts are registered there. They don't have all this compile time stuff, right? That means, first of all, there's probably in Flash some vector of function pointers that again are in RAM that then point back into Flash to wherever that thing goes. Updating those function pointers is an area where I've found many bugs in other libraries, not handled well, but just the sheer latency of going through one extra step, right? Going through one extra dynamic call, obviously killing all machine analyzation of this, right? The interrupts are not, in assembler, you don't know which interrupt handler is going to be called, right? You have a function pointer. And it is known at compile time, right? It's just they don't have the way to express that in their language. Well, they do have macros, and that's the other approach, just some giant macro voodoo. But that has its problems too, obviously, and that has its limitations. I would like a policy that just says, hey, put this interrupt vector table either in Flash or put it in RAM, because almost every microcontroller that's younger than me will run faster than its Flash fetch speed, right? Because Flash is cheap, but it's slow. And so usually what you do is you grab a giant chunk of Flash, because usually you need this, and then the next, and the next, and the next, and now and then you have branches. And so essentially on even a 30-cent microcontroller, you're going to have an instruction cache, and you're going to have instruction cache misses. As in, if you branch somewhere where you don't already have that block of Flash, then you are going to wait till that block of Flash gets fetched. Many, many instruction cycles, right? And you don't so much have that with RAM. RAM often runs something like half the clock speed of the processor or something, the RAM bus. So it's super fast, which is why RAM is most of the cost of the processor, right? If you look at a microcontroller and you look at the version of that same microcontroller, same cord, same periphery, twice as much RAM, that thing's going to be almost twice as expensive. You're almost just paying for the RAM and all the rest comes free, right? So, yeah, if we put this vector in RAM, because we need super low latency interrupts, then we are not paying for that cache miss, because the interrupt service chain is not going to be in the iCache, right? It's going to be somewhere, and not going to be near where what the thing I was executing is. So instead of paying for 2 iCache misses, I'm paying for 1 iCache miss and 1 RAM access by putting the interrupt vector table in RAM. Because where the thing actually is in Flash, well, that thing's going to be an iCache miss, quite probably. But I'm not paying for the iCache miss of finding the interrupt vector table itself, right? And I would also like a policy of, just drop it into the composition of saying, hey, this super short and super low latency interrupt service routine, put that in RAM too. So I don't pay for that iCache miss either. I mean, this is hardly ever done. I mean, people pay way too much for microcontrollers to have super, super, super fast interrupt latency when what they should be doing is putting their interrupt vector table in RAM. But that means they have to touch startup code, which is written in something that pretends to be C and is probably just some voodoo ruins that some chip manufacturer, yeah, I mean, I don't get, just as a side rant, I don't get why chip manufacturers don't auto-generate their startup code. Like, they know, I mean, they have the data sheet. That data sheet's not written by hand. That data sheet's being generated because there's like 50 different versions of that processor, and they're not writing all of those 50 different versions by hand. So they have the data. Why don't they just generate the startup code rather than writing it by hand? Because, again, that stuff's pretty full of bugs. And it's also pretty complicated. And for some, novice programmer to say, hey, I want faster interrupt latency, oh, I have to go hack into this thing that I'm not even supposed to be editing in the first place to make this work. Okay? In our framework, it would be a policy class that you would drop in somewhere to the composition, and it would just put it there. Right? So we're activating efficiencies which theoretically could be used, but I mean, if you look on GitHub, I mean, okay, some stuff's hard to search for, but if you look for some of the special assembler instructions on GitHub, you're not finding much. And if you do, it's usually some student's project that's wrong. Okay? Another thing that's very interesting, which we have not activated yet, but we could with the whole special function register wrapping domain-specific language is, nobody uses the command load multiple, store multiple for special function registers, even if there are two that are next to each other. Well, why not? I mean, it's an efficiency game. Because the language forbids it. The semantics of volatile say, loads in order. We can prove that it's not going to change the outcome because we know everything about the registers. We could implement this as an as-if rule. Because with our domain-specific language, we don't have the semantics of volatile. We have the semantics of our domain-specific language. So we say, okay, you can't take anything away, and you can't reorder things past this point or this point. Within that area, reorder all you want. So, put UART in configuration mode, configure it, 5 things, I don't care about the order, take UART bat out of configuration mode, right? Got to be sequence points here, doesn't have to be any sequence points here, right? We can do load multiple, store multiple in here. We can merge things in here. We can sort by address here, which doesn't sound like an optimization, but if you're on a processor with a 16-bit wide bus, a 32-bit wide bus, but 16-bit instructions, and you have to load a 32-bit address, that's several instructions to load that 32-bit address, right? If you have an address that's somewhere near that, you have one instruction, which is load with offset, where you can put up to 11 bits of offset into your load. It only works if the things are next to each other. If you sort by address, the probability that things are next to each other goes way up, right? So if you say, oh, I have power register, clock register, this, that, interrupts. Oh, interrupts is up here next to power clock. This, that is somewhere in the local storage of that peripheral, further away than the 11-bit offset of load with offset. So I have to load that address again, right? If I put this above that, then it would work because, if I put the power clock and the interrupt priority next to each other, then I can use the load with offset. But as soon as I have the operations that I'm performing on the special function registers in a compile-time readable format, and this is sort of a member of each one of these drivers, I can take all of that and merge all of that at startup, right? So you're touching power clock, you're touching power clock, you're touching power clock. Let's put all those together. And I can get flash footprint shrinks of like 10x against C, because you can't express that in C. Right? So not only can we make C++ the more efficient language as far as RAM use, as far as flash size, as far as interrupt latency, as far as essentially every metric, we can also take the vast majority of the errors that plague our domain off the table. We will get some new problems. We will have longer onboarding at first. We'll have to make a whole lot of libraries. But I'm convinced that we're going to get the same kind of programmer productivity gains that we got by the RAI paradigm and smart pointers, for example, right? Like, you know, back in the day, I give you a pointer, I return a pointer. Do you own that? Do you not own that? That's documentation. Reading that documentation, that's programming discipline. Everything sucked, right? Today, I return you a unique pointer. You own that thing. No documentation needed, right? We took that off the table. It's not a problem anymore, right? Okay, it's a common legacy. That's legacy's problem, right? You know, there aren't a whole lot of examples of places where we just categorically took things off the table recently. We've apparently been getting worse at it. But if you go back far enough, essentially, higher level programming languages in general took things off the table, right? I mean, to this day, students learn how to sort things, right? It's probably good that they generally know how to sort things, but maybe it's not good that they know like all the methods of sorting things, especially the ones that don't play nice with modern caching architecture. I mean, that's programming archaeology and not computer science, right? Because that's a solved problem. I mean, we have generic containers that do that for us, right? We have things that do that for us and we don't have to think about it anymore. And I want to do that in a lot of different things in the embedded domain, because even though we haven't done a lot of it over my lifetime in C++ in other domains, we have done some. And in embedded, we haven't done any, in my opinion, right? I mean, it's essentially as easy to shoot yourself in the foot with a modern C-based, you know, STM whatever library as it is in C back in the day, if you were to program everything yourself bare metal, right? The problems may be less frequent in many cases if you're using, I don't know, threads or, you know, some kernel rather than writing your own super loop or whatever. But they're less common, but they're also harder to find and harder to fix, right? So you're moving problems later in the development cycle. You're not spending less time solving problems, right? So yeah, my hope is that with the modeling power that we have made possible within C++ and the new sort of paradigms and libraries that we've been developing, and the, you know, kind of the rethinking of this entire domain, we can eventually present something which is easier to use than Arduino or Qt or Node.js or whatever, but is also faster than you could probably write yourself, even if you were allowed to write it in assembler in your entire lifetime, right? Because every expert can take their knowledge and put it in here, and the sum of all experts' knowledge generated by a machine is probably going to still be faster than anything you could ever write yourself. So yeah, that's our goal. Definitely come to EMBO if anything is interesting, as in, even if you don't work in embedded, if you want to watch people tear their hair out about reinventing programming or that kind of thing, or just like TMP guys or library design guys or generic thinking guys or formal proof guys or anything like that, come to EMBO. It's close. It's soon. We still have some tickets. Or you can find me on Odin the Nerd at about anything.